All right. Kinetics, when you look at what the reaction depends on and how whatever it depends on alters the speed of the reaction, then we get insight into the mechanism of the reaction. Because the speed of the reaction is going to depend on the mechanism. What the mechanism is just a detailed, picture of what's going on in the reaction. That is, when we look at a simple step in a mechanism, a simple step is going to have, the initial, called reactants. And then it's going to go through some kind of transition state. It could be, so we call it transition state. Then it could fall down into products. Let's say A, B here. But the problem is in a lot of chemical reactions, there are many steps in the mechanism. And so those steps you don't see because you just see, given enough time, what are the final products. And so this would be, a simple step one, but there could be multiple steps. And so after this happens, we have to excite this product, let's say. And then this drops down to C. Here. And then later on, this reacts with some reagent D, let's say. I should have done my lettering differently, but it's okay. And let's say this reaction with D has some strong bonds that need to be broken. And so when we look at the transition state here, this CD, it's quite high in energy. Then ultimately we're back to where we want, and maybe where we want is the product E. And so we might have a reaction like this. This reaction would be an AB plus D yields E. And so that's what we write as far as the equation goes, but hidden within this reaction here are multiple steps. And each of those steps details what happens. Here, for example, this would be an excited AB star, let's say. It's hit. It decomposes into a C plus D. And so when we think about this, we think, hey, the rate is going to equal what? Looks like the rate's going to equal KAB, right?
They're all 1 to 1.
D. It's all 1 to 1, And so if I think about it, AB collides with D. And so if I double the AB concentration, the rate should double because I should have twice as many collisions, right? If I double the D, rate should double as well. So it should be first order in AB and first order in D. But when we have a net reaction, this is the net reaction. A net reaction is the sum of a bunch of simple steps that we don't usually write here because we just wait until we get the products. But in reality, the rate of this reaction is not related to the way the net reaction is written. The rate of reaction is going to depend on the biggest hump here, And so this would be like if you're bicycling along, you know, we got to worry about this hill here the most. Yeah, this will be the bottleneck here. This is going to have the largest activation energy, and therefore this step, step 3, should be what we call the RDS. Right? And step 3 depends on the concentration of C and the concentration of G. And so we're interested in the collision between C and D. It just so might happen that this, by coincidence, is the same because the concentration of C depends on the concentration of, oops, I made a mistake here. A plus B, this should be A plus B. This should be B. And so when we look at,
But what happened to Z?
C, yeah, where is C? I don't see any C here. Yeah, C is what we call an intermediate. Intermediates are produced and consumed within the net reaction.
Are all spectators considered intermediates?
This is not really a spectator because this is actually going to participate. Spectators,
That's right.
yeah, an intermediate is a little bit different because it's eaten or consumed and then spit out again. Yeah. And so the problem is we don't see this because what we see usually is we see the net reaction and not all the simple steps that are involved. This would be a 3-step process. What's that?
RDS.
RDS stands for rate determining step, the slowest step.
Thank you.
Because when we compare it to the other activation energies, they're a lot smaller. And so by looking at the rate law, we can get insight into, you know, what the RDS must be like or what it's related to.
Is the RDS always going to be the highest activation energy or the slow step?
The highest activation energy is going to have the slowest step because it's going to have the smallest population. All right, so what we're going to do is we're going to look at 3 simple mechanisms here. There are more, but 3, you know, simple example mechanisms. Just use the ones from your book. So the first mechanism we're going to look at is a 2-step mechanism. And it's going to look like this. H2 plus 2 ICLs yields I2 plus 2 HCLs. So let me write that over here. So H2 plus 2 ICLs yields I2 plus 2 HCLs. These are all gases.
Oh.
What kind of reaction is this? What does it look like to you?
A redox.
Yeah, it's a redox reaction. All right, the thing is, the question we have is this a 1-step simple mechanism? So, is it a simple 1-step mechanism? Or a more complicated multi-step mechanism? Okay, if we assume that this is a simple 1-step mechanism, then it's simple. The rate law is simple. So first, let's assume it happens in a single step. This would be called an elementary process or a simple step. And so what that requires is this. It's going to require, you know, the H2 to collide with two ICLs. This is called a termolecular process. It's termolecular because three molecules have to collide. Okay, there's a
Don't they have to align right and all that kind of stuff?
Right.
Not really.
three molecules must collide. Okay, but there's restrictions on the collision to be successful. So for reaction, we need the collision to have, it's got to have high enough energy, right? The energy's got to be big enough. Sometimes we don't have to get it all the way to the activation energy, because as we're breaking the bond, we're also forming new bonds, so that could lower it. But, you know, if it's got strong bonds, then we need a lot of energy. And so we have to have enough energy, right, in the collision. And the second thing is, it has to be in the proper orientation. And so what are we trying to form? We're trying to form I2, right, and HCl. And so what I need to do is, maybe I need to line up the imines. Let's see what the transition state might look like. And so if these collide like this, let's say this ICL is moving this way, this ICL is moving this way, then what I can do is I can start forming the I bond here, and the Cl-Cl bond, and then start breaking the ICL bond, right? What else do we have to form? We have to form HCl, so we have to have an H2 molecule going this way, right at this exact perfect time, so that the H's can line up with the Cl's and break the HH bond. This would be what the transition state might look like here. How probable do you think this is? You know, that all the molecules are lined up perfectly, they have the right amount of energy? How probable do you think that is? High, yeah, not, it's actually kind of low probability. I mean, termolecular can happen, depends on, you know, the orientation restrictions. If the orientation restrictions aren't so high, then yeah, it's sure termolecular. But if you got, you know, restrictive orientations, because you got to think, you know, even though we have a lot of molecules, getting them lined up perfectly and moving in the right direction is going to be low probability. And so this is low probability. But the rate, if we assume that it's a single step, then the rate is quite simple, because, you know, there's one step here. And if there's only one step, then we're going to go straight to product, which is I2 plus 2 HCl's. And so there's just going to be one hump. So we start off here, there's going to be one hump, and then it's going to drop down to the product. Let's say the products are more stable. So we've got H2 plus ICl plus ICl. This is going to I2 plus HCl plus HCl. All right, this thing, the transition state, is going to be at the top of the hump here. You know, so a transition state is not the same thing as an intermediate. This is just fleeting, you know, it's transitioning from one set of substances to another. And so this is going to be high energy, unstable, going to decompose. And the energy it's going to take is EA. This energy here, what do we call this energy?
Oh,
Yeah. that goes from reactant to product. Under constant pressure, we call it delta H or delta U. Under constant pressure, is it delta H or delta U? So delta H. Under constant volume, we use probably delta U, more convenient. What's that?
What's the main difference here?
Delta U's for do you remember constant volume, bomb calorimetry versus constant pressure, coffee cup?
Oh,
The difference is work, right? And so we got to account for work between the system and the surroundings. So anyway, if we do this under constant pressure is going to be a lot easier than doing it in a bomb. It's going to be delta H. So this is it. If we were to reverse this reaction, the activation barrier is quite high, because if we were to reverse the reaction, it has to climb up this hill, and it would be endothermic overall. And so going backwards, we have a much larger activation energy, which would start down here and go up there, and the delta H would just be the opposite. Well, termolecular, what we have to do is we have to look at the experimental rate law. From experiment, an experiment is always what you're going to compare yourself to, but from experiment, the rate is equal to KH2ICL. The rate is equal to KH2ICL. And so what it shows is it shows a first order in H2 and a first order in ICL. So if we double the ICL concentration, the rate of the reaction only doubles. Whereas over here, if we had a single termolecular step, then the rate of this reaction would equal KH2, and then we have two ICLs. Let's say we have this left ICL. So if we double the concentration of that left ICL, it should double the rate. And then we have the right ICL. And so in other words, this should be KH2 ICL squared. Because when we double the ICLs, we're going to double both the left and the right, and so the collisions quadruple. This rate law does not agree with experiment. And so we can discount this mechanism. This does not agree with experiment, and therefore this mechanism is not correct. Mechanism is not correct. So, well, what is the experimental rate law? The experimental rate law is given here. And so this experimental rate law is going to give us insight into the mechanism, right? We should be able to figure it out. And so whatever mechanism we come up with must agree with the experimental rate law. And the overall reaction. What we say, if there's agreement between the mechanism and the experimental rate law, we say that the mechanism is consistent with the experimental observations. So the mechanism is consistent with observed rate law. But there's a possibility that multiple mechanisms are consistent with the observed rate law. There is the possibility that multiple mechanisms, different possibilities, multiple mechanisms might be consistent.
Okay. The question is, how are we going to consider those possibilities?
Or eliminated.
How do you, additional observations are required to either prove the mechanism or to eliminate. And so additional observations are required to prove the mechanism. What kinds of observations? Well, people try to observe the transition state, for example, by high-speed spectroscopy. And so they might be able to see certain, because this is going to change the electronic, what's happening with all the orbitals here. It's going to change the electronic energy levels, and therefore it's going to absorb light differently, right? And so people try to observe these things and see if they can prove. Well, okay, what we're going to do is we're going to guess a mechanism, and there are three types of collisions that are common. And so let's try to guess. I'm just going to call it guess because essentially that's what we're doing. We're going to guess a mechanism for that reaction that would be consistent with that rate law. And so when we guess this mechanism, we have three types of collisions that we're going to consider. The most common collision would be something like a bimolecular collision, just two molecules colliding, right? A and B. So boom, or two A's or whatever, bimolecular. So bimolecular would be something like this. Okay, we have three molecules possible, right? And so what are some simple bimolecular collisions that would result in a fundamental step or fundamental process? And so I would say maybe an H2 collides with a ICL, right? An H2 collides with an ICL, boom. That would be a bimolecular. Or, what's another possibility? An ICL collides with an ICL. It's another possibility. Well, due to the stoichiometry of this reaction, those are the only two bimolecular possibilities that we have. Now, we have to use a little bit of chem to figure out what we're going to form from these. And so if you have a H2 collide with an ICL, what do you think might form when they collide and bonds are broken and new bonds are formed? What do you think it might form? What?
Could it form an HCl and an HI?
Yeah, that's perfect. I would say maybe an HI and an HCl. Those look reasonable, don't they? But yeah, sometimes when people do this, they come up with some of the most bizarre things that don't seem so reasonable. Like, for example, they might come up with this, like something like an H2 ICL, an H2 ICL molecule.
It's not stable.
Well, what you want to think about is you want to think, can you draw the Lewis structure for it? Something like that. All right. Or if we had an ICL and an ICL collide, what do you think might form from this? Kelly?
Iodine gas and chlorine gas.
Yeah, exactly. And so that's not too bad. Now, these are one step. And so we're going to call these both, these are fundamental processes. And if they're fundamental, there's no hidden steps. So if I double the H2, then the number of collisions double, therefore the rate of the reaction should double. If I double the ICL, the same thing. And so the rate is just going to be dependent on the coefficient. This is a coefficient of 1, this is a coefficient of 1. And so the rate for these types of reactions is K, A to the little a, B to the little b, etc. And so in this particular instance, it would be K times the H2 concentration to the first times the ICL concentration to the first. The reason we have to use M and N here in general is because we don't know if it's a single step or if there's anything hidden in there, right? But here, I'm telling you, there's nothing hidden there, and therefore, what you see is what you get, and therefore, we can easily come up with the rate law. For this other one, the rate is going to equal what? The rate will equal K ICL on the left times the ICL on the right, which is going to give us K ICL squared. And so here, if I double the ICL concentration, I'm going to quadruple the speed of the reaction. That's bimolecular. We did termolecular already. And the other one that's possible is unimolecular. Unimolecular. Now, how do you have a unimolecular collision?
What?
A unimolecular collision. What would a unimolecular collision look like? Two molecules of the same type would be considered bimolecular, like two ICLs colliding
About like a
together.
disassociation with the H2 and you lose an H or something like that?
Yeah, something like that. What unimolecular is let's say there's a wall here. And so let's say the H2 collides with that wall and breaks apart into two H's, let's say. Or let's say that there's an ICL here, and let's say we're not doing it in the vacuum, let's say we're doing it in air. And so what's the most common molecule in air? Nitrogen. And so does nitrogen participate in this reaction? No, but there's plenty of nitrogen around. And so let's say the ICL collides with the nitrogen and then breaks apart. These would be examples of unimolecular, you know. And so the way we do it is, well, we have two possibilities for unimolecular. The H2 might break up into an H and an H. Two atomic hydrogens. Or this is what we call homonuclear bond breakage. Or it could be heteronuclear, an H plus and an H minus. Which one do you think would be more stable, homonuclear or heteronuclear, a bond breakage?
Hetero.
Probably homonuclear, right? So you see the charge, you're generating a charge here, voltage. Or ICL, of ICL, what would that do as far as unimolecular? I mean, you can't do much. Well, this is what I see all the time. I see I minus and Cl minus. A lot of people go, okay, it's going to break up into an I minus and a Cl minus, but you know what? You know, so many people do not care about charge. If you're a nuclear chemist, that's okay because, you know, charge is generated quite easily from radiation. But, you know, for chemists, charge is everything. And so for a chemist not to write down the charge of ions is, well, it's very bad because the most important force in chemistry is electrical forces, i.e. charge. And if you can't get the charge on there, then you're missing something. And so pay extra attention to charge. You know, a lot of people, they don't care about charge, so this looks perfectly normal to them. But when I look at this, this is terribly wrong, right?
If you're going to guess which one would have the positive charge, would you put it on the I or the Cl?
Well, if you're going to put it on the positive, you put it on the more electropositive.
Yes.
The more electronegative element should get the negative charge, typically. And so which one would get the positive charge here? Iodine. Right. Or, you know, that's creating, does that look so stable either?
Isolus.
No, it's probably going to be a homonuclear. That is, it's going to just form iodine radical and chlorine radical. So just break the bond right in the middle, rather than creating charged species. And so, most likely, the radicals are going to form here. The radicals would just have an unpaired electron. But anyway, the rate of the unimolecular is just going to depend on how much hydrogen we have. So the rate is K, the H2, right, to the first. The rate of this is just K ICL. So we're going to propose this mechanism for this one. The mechanism that we're going to propose looks like this. This reaction is going to happen in steps. And so we call this step one of the mechanism. Step one of the mechanism, out of those, which one do you think we should go with? Well, probably, the thing is, like hydrogen gas, when you think about hydrogen gas, do you think it breaks apart easily or doesn't break apart so easily? It's very reactive, but do you think it breaks apart into radicals easily? It's like nitrogen. When you breathe in nitrogen, are you breathing in nitrogen atoms or are you breathing in nitrogen molecules? How many nitrogen atoms, like radicals, are you breathing in? None, pretty much, because it's stable. And so I would say, these, H2, it could happen, right? But unlikely. This one, yeah. These would be more likely here. And so out of these two, which one will we go with? The two ICLs colliding or the H2 and the ICL colliding? It doesn't really matter. We just trial and error and then guess. But I'm just going to guess the H2 and the ICL collide. This is going to form HI plus HCl, right? But, this seems totally reasonable, but you know what? There are other possibilities for products. Can you think of other possibilities? Well, actually, let's just go with this, and then we'll think of other possibilities. Because, well, we'll just go with this. All right, what's the rate of this step? The rate of this step is just equal to K. We're going to call it K1 for step 1 times the H2 times the ICL. Okay. Well, if you look at that, compare this to the overall rate, the experimental rate, and what do you see? They're the same, right?
Yeah.
And so what we're going to do is we're going to call this the RDS, the slow step. And so it doesn't matter how fast the subsequent steps go, the rate of the reaction is not going to be impacted by step 2 because step 2 is going to be faster, or step 3. The slowest step is going to dictate the rate of the reaction, which is going to be this. And so if this is the RDS, then this is equal to the overall rate of reaction. Right? Right. And so we're done. Except,
How do you determine if a mechanism is correct or right now?
well, we don't, in order to determine if it's correct, we'd have to measure an intermediate. Do you see what an intermediate is in this? Because when I look at this net reaction, am I producing HI or HCl? I'm not producing any HI, am I? All right? HI shouldn't be there, and so this is not done. Because HI is what we call an intermediate. Correct?
But how do you know
Yeah.
HI is an intermediate?
Because when we look at the overall reaction, what are the products? The overall reaction. What were the products of the overall reaction?
HI and HCl.
No,
I2 and 2H.
I2 and 2HCl. There's no HI. And so we call this an intermediate product. We have to get rid of it. It's an intermediate. And so that's okay, we can get rid of it because if an HI collides, we have two ICLs, so we need to react another ICL. If an HI collides with an ICL, what can form? I2 and HCl. And so the intermediate here is consumed in the overall reaction because when I look at the overall reaction, I add up step 1 and step 2 to get the net reaction. The net reaction is going to look like this. It's going to be H2 plus 2 ICLs. This yields I2 plus 2 HCl's. And so it doesn't matter how fast this step goes, it's faster. And so the overall rate's just going to depend on the bottleneck. And so that's what we have here. Uh-huh.
Why did you say that's the slowest step?
Why?
Or you have to use arbitrarily?
Arbitrarily. I'm just guessing. If step 1 were the slowest step, then this would be the overall rate. Well, it just so happens that the overall rate is the same as this, right? And so if step 2 were the slowest step, then we get a different rate law. All right, so the one type of reaction you're going to get is a reaction where we have a multi-step mechanism, but the first step is the slowest. If the first step is the slowest, then the overall rate is just the rate of the first step. It doesn't matter. I could have step 3, step 4, step 5. As long as step 1 is the slowest, then that's all that matters. All right, the next mechanism you're going to see is one in which the second step is the slowest. So what if the second step were the slowest? Here, then the rate law would be different. If the second step were the slowest, then the overall rate should be equal to K2 times the HI times the ICL. Does that match the experimental rate law?
No.
No, not even close. Hmm? Yeah. Or we other way around. We're given the mechanism and then we figure out the rate law. Or we're given the rate law and we figure out the mechanism. Okay? And so right now what I'm going to do is I'm going to give you the net reaction and I'm going to give you the rate law. And then you have to come up with a mechanism. And you coming up with a mechanism is just guessing game. You know, we have unimolecular, bimolecular, termolecular collisions. And then you go through all the possibilities. And then you see, you know, can we get the experimental rate law from those? All right, so the net reaction for this is going to be 2 NOs. In this next example, 2 NOs plus an O2 yields 2 NO2. The experimental rate law looks like this. The rate is equal to K NO squared O2. So it's second order in NO and first order in O2. And so think of some collisions that you could do as a possible mechanism.